the details are quite hard. So if you look at this directly from above as a contour map, then you can see it's around here, the maximum value. Yeah, and you can see what it's going to be. It's going to be quite small, it looks like. Yeah, because mostly it's negative. It just comes up to about here. So what you want to know is, how can we isolate this and tell whether it's a maximum or a minimum? So here's another map, and here we're thinking about gradient vectors. So the gradient vectors are just the vectors with the partial derivatives of h in each direction, x and y. First need to find some derivatives. Let me display it. Okay, so here it's calculated the gradient vectors at various points. So it's differentiated it here, and then it's substituted in various values to find the partial derivatives with x and y and drawn those as vectors. Right here. Okay, so with a single variable function, you estimate how the function is going to change by multiplying the gradient by dx, and it works whether you move forwards or backwards. So that's why up here I mentioned that you can use the same 2, 2, 1 going forwards or backwards because there's only one gradient. The problem with this is that here we have the problem that if we start here, there are an infinite number of different directions we can go in. Linear algebra helps us get around this a bit, because if we take the dot product of dx dy and this gradient vector, that gives us the change dz. So that's this equation we had before. So this times this gives us this, which is our estimated change in the function dz. Okay, so if you look above and start off at the base of any of these, if you start at the point 10, 48, if you move in any direction, the gradient vector shows you what's going to happen to the function. And the more similar the direction of the two vectors, the larger the dot product. So if you start from 1048 and go southeast, so 10, that's this one here, I think. Yeah, 1048, that's this one. So if you go southeast, then it's going to increase very sharply if you go in this kind of direction, because if you head in this direction, then the dot product of your direction vector with this vector, so if dx dy is the direction you're moving in, dot product with this vector will be very large. If you head in this kind of direction, so northeast or southwest, then there'd be very little change in the function because they're almost at right angles. So the dot product will be very small. If you head this way, the angle would be obtuse between the direction you're travelling in, dx dy, and the gradient vector. So then you have negative answers because going in this direction, the value of the function is decreasing. If you go exactly 90 degrees, there'd be no change in the value of the function. You're going along one of these contours. So heading at 90 degrees, the dot product will be 0, meaning it's not changing at all in that direction. What you're trying to get at is, what happens to those estimates as they move away from an initial point? If the estimate is falling, then it means it's concave in that direction. If it rises, it's convex. And we want to find a point where it's either convex in all directions or concave in all directions. So d2z is the way that the predicted changes are changing themselves. Okay. Unfortunately, there's many different directions to go in, so it's complicated. So really, just take that in. Don't worry about this part. You get a few people that really want to know how the nuts and bolts work, so I should try and explain the nuts and bolts. But for many people, this is really complicated, especially the first time you see it. So what I want to know is, how does this differential change between the initial point and the point we end up at, which is x plus a little change in x, y plus a little change in y, and dx and dy can be positive, negative, any combination, because I can move in any direction. So dz, with this starting position and this move, has this formula. It's the partial derivative with respect to x times how far I go in this direction, plus derivative with respect to y times how far I go in this direction. I started using f instead of h because that's going to be more general and comparable to books and so on. So if I move on, starting from this point, from here I predict what's the change from here, then it looks like this. It's the same formula, except I'm starting at x plus dx, y plus dx. So what I want to know is that d2, this change in this, is going to be the difference between this and this. So I've got to subtract these two things, which is why it gets quite large. So the difference in the predicted change is this minus this, so it's all of this stuff. So you can see, really all it is the change in each, the difference in each partial derivative multiplied by that differential. Okay. Now, all you do is to replace these estimated changes in the first derivative using the second derivative, because I can estimate what's going to happen to the, I've got an estimated change in the first derivative here, is equal to second derivative times half on the next, second derivative in the y direction times this. Estimated change in the y derivative is the same thing again. How's y going to change going to x? How's the derivative going to change going to y? So differentiate again times y. Okay, and then these things here, I'm going to substitute back into this, into the right hand side. So this part, this bracket, I'm going to replace by this part here, and this bracket is the estimated change in Fy. This part I'll replace with this here. So you end up with this. So the linear estimate of the change in dz is partial derivative with respect to x plus times dx plus times dy and so on. I won't read them all out because you can read them. Then one more thing you've got to note is that this and this are actually the same, because the order of differentiation doesn't matter. You can check that yourself if you like. If you differentiate first with respect to x and then y, you get the same thing as if you do it the other way around. So this is the same as this. So if you multiply it out, you get this equation. So it's f of x times dx is that. So fxx times dx, dx squared. fyy times dy plus 2 of these fxy dy dx. Oh, sorry, dx dy, that happens to get 2 of those there. And this is the basis for the tests. So if this is negative everywhere, it means that in any direction you go, the predicted change is getting smaller. So it must be concave. So you must be at a maximum. If this is getting bigger everywhere, you know that in every direction you go, the predicted change is getting bigger, so you must be at a minimum. And if it changes differently in different directions, then you can't tell either. It could be a point of inflection. Okay, now the problem is, how do you do that? It's not quite as simple as in the how do you tell that this is always going to be positive or always going to be negative for any value of dx and dy? Because unlike the first example, with one variable you just got dx squared, which is always positive. So you just look at this. But in this case, these things could be negative. So if one is positive and one is negative, this could be negative. In which case it's hard to tell from just these whether or not the whole thing will be positive or negative. So what you do is you put this equation, f, into matrix form. And you get this. Now you should be able to check by hand that this gives you the same thing as f. There's one of the problems on the worksheet from linear algebra that looks very much like this. So you have a transpose vector times the matrix times the vector. Multiplying this out gives you this equation up here. We can do it by a computer if you want. It's cheat. Multiplying that gives you that back. Now, this matrix is called the Hessian matrix of second order partial derivatives. And with matrices, when you have a square matrix like this, it is possible to tell whether or not the result of this will always be positive or always be negative for any values of d or dm, dx and dy by examining the matrix. And the rules are that, and here we're getting, if you've been drifting through this, this is the bit you need to know, that if the top left entry of this is positive and the determinant of the whole matrix is positive, then this matrix is called positive definite. In that case, this answer will be positive, whatever you put in for dx and dy, positive, negative, doesn't matter. If this is positive and if the whole determinant is positive, then this will always be positive. Meaning that whichever direction you go in, the estimators are getting larger, so it must be convex, so you have a minimum. Unfortunately, the opposite one's not quite the same. This needs to be negative, and again, the whole matrix positive. In that case, the matrix is negative definite, and this will always be negative, whichever direction you move in which case the estimates are getting smaller as you move away from the maximum, so you must be at a local maximum. So here's general formula. So the rules for d2z alpha single alpha just for like the single variable case. So if this is positive, you have a minimum. If it's negative, you have a maximum. But the way you tell that is by looking at this matrix. And if m is negative definite, you have a maximum. If m is positive definite, you have a minimum. So before we go on to 3 or more variables, just have a look at function 8. So this is how you do function 8 from the start. You'd write down the first order conditions and find a solution. So that's okay, that's a candidate for it. But you don't know if this is, you don't know yet whether it's a maximum or a minimum. So you make the Hessian matrix. You should be able to see how this comes out. So this comes from this. So this is the first derivative with respect to x. So differentiate again with respect to x and you find -4. Differentiate with respect to y and you find 2. Start with this one. Differentiate with respect to x, you find 2. With respect to y, you find 2. So these are the second derivatives of the derivatives for x and y. Now, because this is negative and the determinant is positive 8 minus 4 is 4, which is positive, so it's negative and then positive. That means the whole matrix is negative definite, which means that this is negative in any direction. So in any direction you go, the slope is decreasing, so you must be at a local maximum because this is negative. So negative definite, local maximum. It's a local maximum because in this case you can see this matrix never changes. So it's concave everywhere. It's not just one point. So it must be a global maximum as well. So all agrees with the graph. The function of it seems to show that it's definitely going to be a single maximum point on a concave surface. And then finally, to generalize this, if you had 3 or more variables, you just make the matrix with a more partial derivative. So if you had a function of w, x, and y, then you have a matrix like this. So for this, for a positive definite matrix, so it's going to be a minimum, that's going to be positive. And then, I can't shade it, but the 2 by 2 matrix you get if you eliminate the bottom row in the right hand column, so just w, w, wx, wx, and xx. This has got to have a positive determinant, and then the whole thing has got to have a positive determinant. So if it's positive determinant, then the whole thing is positive definite, so you have a minimum. If on the other hand, this is the fiddly bit, if this is negative, if the 2 by 2 is positive and the whole thing is negative, so it alternates negative, positive, negative, then it's negative definite and you have a maximum. And then more than 3, it generalizes the same way. Positive definite, so everything has to be positive. Negative, it must alternate. So that's how it works. But I won't ask you to calculate anything with even 3 by 3 in the exam for optimization because that would take too long. So for now, thanks for watching.